In this lesson, we're going to look at triple integrals in cylindrical and spherical coordinates. Let's start with cylindrical coordinates, and we have a point in three-dimensional space, and here's our point. And you can see that if we start at the origin here, and we reach out a distance r, and that would be initially reaching out on the x-axis, and then we rotate an angle theta, and we end up at this point down here, and then we rise up a height of z. So our coordinates for this point in cylindrical coordinates will be r, theta, and z. Well, we've seen r and theta already from polar coordinates. When we look at this right triangle, here we have our y distance here to the point on the xy plane, and our x distance here. And what we can see is that we have this right triangle. Here's our right angle. Here's our angle theta, and r is the hypotenuse of this right triangle. So we know that x squared, this is a Pythagorean theorem, plus y squared is the hypotenuse squared, or r squared. And from this, I know that r is equal to the square root of x squared plus y squared. Now I also know, and this is really from polar coordinates again, because I'm now looking just on the xy plane down here, that if we use the cosine, we can say that the cosine of theta is the adjacent side, which is x, over the hypotenuse, which is r, and the sine of theta is the opposite side, this is from the angle, over the hypotenuse, which is r. And if we solve for r, actually if we solve for x, we get x is equal to r cosine theta, and if we solve for y, we see that y is equal to r sine theta. So we know that we can write this down. This is for our conversion. X is r cosine theta, and y is r sine theta. Now we can see that this height, that x and y give the location of the point on the xy plane, and z tells us how high we go up. So in this case, z is simply equal to z. And this means if we are trying to find our x, y, z coordinates using our r, theta, z polar coordinates, we use these three equations. Now if we want to find our r, our theta, and our z coordinates for cylindrical coordinates, well, we know that z is just equal to z from the x, y coordinates. And we know that r is the square root of x squared plus y squared. To find theta, we have to look at the relationship between x and y, because we know that the tangent of theta from the angle is the opposite side, y, over the adjacent side, x, which means if I take the inverse tangent or arctangent of both sides of this equation, I get theta is equal to the inverse or arctangent of y over x. So let's write this up here. To get theta, it's the inverse tangent of y over x. So these three sets of equations allow us to convert between our Cartesian and cylindrical coordinates. The first set of equations allow us to find our cylindrical coordinates from our Cartesian coordinates, and the second set allows us to find our Cartesian coordinates from our cylindrical coordinates. Now let's look at cylindrical coordinates when we're integrating. And when we integrate, if we look at this, imagine I've drawn this diagram where this is our z-axis. I didn't draw the x and y-axis, but you can imagine, let's imagine this is our x-axis, and we are rotating this direction with theta. And so if I just look at a small change in theta, delta theta, and this is my r from the origin forward, and this is a small change in r, delta r, I end up with sort of this three-dimensional sort of sector because I have a small change in z. Let me write a little bit here. So if this coming out here is our x-axis, you can see how we're rotating this direction towards our y-axis, and how we are moving out. R is growing, increasing this direction, so we have our delta r, and our point can be also moving up in the z direction, and we have our delta z. And so we end up with this sort of three-dimensional piece or volume. This is our delta volume, okay? So we'd say we're looking for volume, and we're going to find the volume by adding up, by summing up all of our little delta volumes. And our delta volume, well, let's take a look for a minute. We're going to have to look at the base of this. If we look at the base of this, what we have is a section of a sector. So let me write this in blue. So the base right here, that's right, this is the base. This base is sort of a delta sector. And we looked at sectors in a previous lesson, and we know that the delta sector is r, delta theta. And that gives us this base that we have down here. You cannot see just a section of it, but the base sort of looks like this. So the volume, let's go back to black, is the delta volume is, I could say it is the sort of delta base times the height. Or let's change this up a little bit. Let's say it is the base times the height. It's the base times the height, which is summing up the base, which is r, delta theta, times the height, which is delta z. And we're going to add this up from n equals 1 to infinity. And of course, we want to know what this entire volume is. This is going to give us our entire volume. So for this, we're going to use integration, okay? Because the integration is if we take the limit as n goes to infinity of adding up, of summing all of our delta volumes. And what we do is this becomes a triple integral over our 3D region times, and in our integrand is r, and it's dr d theta dz. So to recap, we're taking this sort of the three-dimensional wedge, which has a base, which is the delta of a sector, and it has a height of delta z. And by adding up all of these wedges, we get our full volume. And let me put that in. This gives us our entire volume.